So, hey guys, welcome to High Entropy. It's another live streaming on DSA, and we are solving the DSA problems. And right now it's 1 o'clock, so very late. Actually, I was planning to start it soon, early, but somehow, as usual, I start using scrolling reel or something, and I forget the time. So it happens most of the time, and you can see my underwear is hanging there because today I just tried to reduce the noise and background noise, so I hope audio will be clear to you guys. Do let me know. And yesterday, to be honest, I was feeling sleepy, so I just stopped the stream. But today, let's try to grind. And one more thing I observed, that it's not about problem solving, it's about whether you are solving one problem with the proper right approach. Because my goal always what I like, my thought process is same. Still I'm thinking in the same way, like, okay, I need to solve the problem, that's all. So you are not I'm not here to basically say, okay, I just it's not like you are doing a government job or something where you just have to finish your task. Here you are learning, and when you are learning, no matter whether you are taking 1 hour to understand or you are taking 4 hours to understand, the goal is simply you should, if you are solving a problem, you should learn everything about it. You should know the corner cases and all. And this is one of the mistake that I'm making. Not only here, even I'm solving the lead code problem on the SQL, then also I'm making the same mistake. My goal is just simply finish the task, and that's not going to help because you will forget something, you will learn something, and it will continue, and you won't succeed. To be honest, this is one of the biggest learning that I need to adopt, or I need to understand that it's not a kind of race, it's a marathon where you need to solve the problems. You don't Some people, you can see, they have solved only 200 problems, but they know very well how to solve the DSA, how to use the data structure, proper data structure, how to recognize the pattern when you are solving the problem. And some people are solving 500 problems, then also, yeah, but it's not like you will get it. Sometimes you need to solve more problems to understand the logic behind it. For example, solving when I was learning this approach, merge sort, I wasn't getting it, and so I solved it so many times. Then after that, I got the intuition behind it. It happens. You have to try it multiple times, but your goal should be always that you need to finish the task. You don't need to. You are not here to finish the task, but learn. It might click in 2 3 watch, or 2 3 times, after 2 3 times or 10 times. That is okay, but don't ever think like, okay, someone is able to solve it in one go, and you also should be able to solve in one go. Everyone has different capability, different mind memory mapping, or the memory capability, and everyone has to go through a different journey. So everyone has different journey. Some You might take 1 minute to solve a problem. Someone takes 10 minutes or 100 minutes, 4 hours. So it's okay. And until and unless you are learning something, that is everything is okay. So nonetheless, ultimate goal is simply to learn the problems, solve the problems, and recognize the pattern. And so today's agenda is simple. I just have to focus on one thing. That's why I started revising the things instead of just moving. Progress is only helpful, or the dynamic programming concept. Simply, it's not about just solving you can learn a lot from the dynamic programming. I feel like it's a pretty intuitive in real life as well. If you are learning something and if you are forgetting, no matter, you won't be able to optimize the things. You have to remember, not remember hardly in memory every question, but you have to remember the pattern. If someone asks like a Bellman Ford algorithm, then you should be able to know what is the Bellman Ford algorithm, and what it does, what are the pros and cons of it, what are the limitation of it. So it's not about, and definitely you need uh, we need lot of practice to solve the problems, because one thing is for sure, that everyone has different journey, so we need to follow our own journey and don't compare with someone else. Everyone has different trajectory, different path. uh, you might be master in something else and they are master in something else, so it's okay. Don't be uh, If it requires, take break and maybe show up but next day. But it's important. Just be confident and keep yourself motivated from any point of view. Don't be uh, don't feel like, okay, some people are able to solve it quickly and I'm not able to solve it, and then how will I'm not in going in right direction. Everyone has different journey, and you should enjoy your journey. So that's all in this video. Bye bye. Take care. No, no, no. I have to solve the problem now. Okay. Let's just say let me save my screen. Okay. So we are here. Mm, okay. Now let's go to the DSA pattern challenge. So one thing, funny thing, I'm sharing here. It's like yesterday I felt like I'm not feeling sleepy. So can you give me some task? And it provided me a question, and I was thinking like it's a simple problem, but it was little tricky. I provided one solution, it wasn't working, was negative numbers, and then okay, let's forget about it and let's do one thing. So here, what is this? So I'm just looking if audio is clear to yeah, but it's clear. Just audio is slow because yes, earlier what I was doing, uh, I was basically amplifying the audio, so that was causing the issue. Background noise was also coming. So let's go to take you forward and let's move forward. Both things are important. So graphs, we have solved BFS, DFS. So BFS and DFS is clear to me. Breadth first search, simply you are using Q. You are basically okay. Let me just recall the things here. So if I talk about DFS, what exactly we are, because I forgot too quickly things like for example I forgot the topo shot. I don't remember. I remember the concept, but I forgot the exact methodology. So I need to recall it. But let's leave it, park it for the time being. So let me first recall the DFS PFS before jumping into the problem. So quick time play. What exactly we are doing in DFS PFS? This is one of the biggest problems. Until I won't solve plenty of problems, then I won't be able to get remember the things. Okay, one thing where is SQL mistakes. Don't look at my okay. Solve it on paper three. So this is 100%. And so first, let me just recall the BFS and DFS. These are very pretty popular algorithms that are being used in tree as well. Tree also. Here we are talking about graph. So in the graph, what exactly we are doing? Suppose you are given a node, uh, basically a network of nodes. So let's say these three nodes: 1, 0, 1, 2. So what exactly we are doing in breadth first search? You start from, let's say this is source node. So you will start from exploring from this node, and you will look for all its neighbors. So you are using breadth first search, basically level by level you are traversing. And in tree also we do similar kind of thing, BFS, depth first search, where you level order traversal is known as breadth first search. But let's forget about tree. Here we are talking about the graph. So every time what exactly you are doing? So simply you are uh, pushing a node, and then you are processing a node. Basically, suppose there is a node. Okay. So what exactly we are doing? We are taking out a node from queue, pull out, and so queue means first in first out. That is okay. Whatever comes first, you can say railway queue, where you are going for tickets or any movie ticket or anything you can compare with. So queue, we are using queue. And here, whenever you are taking out a node, you are looking for all of its neighbor, and its neighbor would be this one and this one. And now suppose you moving, and you are keeping a visited array, visited. If the node is already been visited, you don't want to reprocess it, right? For example, one and two, you will add one. Uh, let's say you will add two. If you are processing node zero, okay, you can think in such a way. Now when you popped out, now you will say one, For 1, its neighbor are 0 and 2. But 0 you already visited, 2 already visited, so you won't visit anything. And from 2 also, you will say its neighbor are 0 and 1. So you will say, okay, this is the breadth first search. And in the depth first search, what exactly we are doing? You start from a node, let's say 0, and from 0 you are going to 1 and 2. So from 0 you will start from node. Let me just draw it with another example. So you start from here, you will look for its neighbors. So its neighbors are 0 1, 1 and 2. So there is another branch as like this. So what you'll do, you will choose any one of path first. You will explore one path. So you'll after 0, you will move to 2, and from 2 you will move to 1. From 1 you will try to move again because its neighbor are 2 and 0. So you will say, okay, 2 is visited, 0 is visited. So that's how you will basically you will explore all the possible options that are nodes, all the nodes that are reachable from 0 to via 0 to 2, and any paths. So you will explore all, then you will say, okay, other nodes and all. So this is the way that we do in-depth first search. You are exploring, basically you take one branch and you start exploring until its final node, and then you start again. For example, suppose there is another node, let's say 0 1 2 and 3. So what you will do, you have two options here. When you are here, let's say you choose 3. So first you will explore 3. After 3 you will say, okay, this part is completed, this part. Now what I'll do, so you are here, you have to explore other neighbors of it. So you will explore this. So this is how you are going to do. So DFS is okay. In DFS, it's completely relying on recursion, and BFS relies on queue. So this is okay. I can recall it quick. Easy, easy peasy. And now let's jump to another. I forgot the topo sort even. What exactly we were doing in topo sort? I remember the concept for topo sort. Let me just think what exactly happened in what we were doing in topo sort. Topo sort, topological sort basically. There was a problem. It was related to, was it related to topological sort or something else? Um, I know there was something where, yeah, I remember one problem. I am not able to recall it. Where what exactly we were doing? Some concept was there, like, okay, you have nodes and you have to split them into two parts, two halves. I mean, suppose there are nodes, so all the nodes in first set 1, and all the nodes in set 2 should be uh, like here. If node 1 2 3, these nodes should not be linked to each other, these nodes should not be linked to each other, but these are linked to here. For example, it could be 1 to 3, this to this. There is a term, I forgot the term name. I solved this problem, even I forgot the solution. That's how, like, that's why we need to, like, when we are watching tutorial, we can easily detect the problem pattern. But once you will move to another topic, after a while you will see whether you are able to still recall, or that's why revision is very important. Okay, so I forgot it. But let's focus on topo sort for the time being. In revision I will get it. Topological, I remember concept of topological sort, what exactly we are doing here. If there are some nodes, so this is being used in DAG scheduling, where you have to decide, okay, this task should be completed first, and then all the dependent tasks should be completed, and suppose there is another task, then it is, suppose once these two tasks will be completed, then only you can complete this, and then this. In such a way, uh, we need we can take help of topological sort. So what exactly we need to do? I mean, I'm just trying to recall the algorithm. So we have graph, suppose 1, Was it directed acyclic graph? I think yeah, it was directed graph. Yeah, then only you can decide which one should be completed first. So let's say this one, this one, this one, this one, in such a way. So directed graph. First thing, you have given directed graph. You have given a directed graph. Sort the node in topo order. Topo sort nodes in topo order. I don't know topo order what actually the term should be used here. So let's say I just have a node 0. It depends on uh, 2, then 2 depends on 5, 5 and 6, 3, 3, some 0, 1, 2, 3, 4, 5, 6, 4 and 0, 1. Where is 1? So imagine this is our graph. I just draw random graph. So you know one thing. First thing is 0 should be completed, and after 0, okay, let's draw it first. So first should be completed 0. There could be multiple. There could be multiple solution. I remember it. Yeah. So let's say I know it's after 0, 4, 2, and 3 should be resolved, and even after that only 5 can be completed, and before 5 1 should be completed. So can I say you can complete 0, 4, 2, 3, 4, 2, 3. You can complete anyone. You can take any order of 4 to 3, and after that you need to complete uh, 6. 6 should come after 2, and 5 should come after 1. You can solve because no. Okay, yeah, 1 you can keep here, and you can keep 5. So you can see 0. Okay, after 0 what should be? Everything come after 0. Now 4 to 6, 4 to 3, they can come in any order. So you can take 2 first, and then 4, then and so on. Then okay, so I take 4, 3, 2, 3. After that, after 2 only 6 can come. So 6 I kept here, then 1. 1 should come after 4 because 4. So this is one option, and 5 should be at the end because it should be after 3. It should be after 1. So it's after 3. It's after 1, and it is after 2 as well. 2 is before it. So this is one of the order. You can create multiple solution. One of the solution can be can have multiple solution. Okay, but now I need to uh, what was the algorithm to sort it? I need to recall it. Oh God, it is like I'm learning something and I'm forgetting also. It's okay. It happens always. You won't remember everything until or unless you are a robot. So, hmm, I'm not able to recall it, I believe. Something was like where we were adding the node at the end, and then we were, uh, are we using a stack or what? Something was we were using. I mean, I didn't know, like when you were exploring, for example, depth first search, only I guess we were using depth first search to solve it. And what exactly we were doing? So, for example, you will say, okay, you start 3, you will say, okay, 3. From 3, you will go to 5. Let me just try to build it. 3, 3, you will go 5. So, 5 is done. So, you'll push into stack. First, you will go to 0. No, no, no. Yeah. So, it was like you are keeping 5 here first because there isn't any node. Then you will keep, like, from here you will start. From here you will start, and you will explore a branch. So you will go to 3, you will go to 5. Once you will reach to 5, there isn't any further nodes that you can go. So from 5, you will once you are returning, you will add this node. So you will add 5, then you will add 3. Okay, then you will move to 0 only. From 0 you will go to 2. So 2 you will go. So 2, before 2 moving to 2, you will go to 6. So 6. From 6 you cannot go further. So you can add it 6. Like you have, while returning you can add it. And now same, from here you have to explore 5, but 5 is already in the stack. You can say 5 is has been already visited. So okay, you won't do anything. Now when you are returning from, you have returned from both, all the neighbors of 2. Then you can add 2 in the list stack. Okay. Now this part is also done. Here you done. You did this one. Now you will go to another, uh, neighbor of 4, 0. So you'll move to 4. 4 will call its neighbor. You'll explore depth first search. I mean, you will deep down into this branch. So 1. After that, you will try to access 5. Its neighbor is 5, but 5 has been already visited. So you won't push it into stack. Then you will say, okay, let me push 1, because you are, once you are returning you can push 1. And after that, once you return from here you can push 4. And now you can see like you completed all the paths, so you can push the 0. So if I draw, now you have to take out one by one. So you'll say 0, then you can say 4, 4 to 1, 1 to 2, 2 to 6, 6 to 3. Let's see, and 3 to 5. So this is one of the topological sort. I'm just uh, checking. 0, 4, 1. Everything is okay so far. No dependency on anything. So okay. After that you said 2. Okay. 2 and these 4 and 1 has no dependency, so you can keep them anywhere. 6. Yeah, 6 is okay. After 2, then you are going to 0, 3. 3. 3 is okay. Then you are saying 5. So 5 is coming at the end. So everything is perfect. So I remember topo sort also. I mean, I'm able to recall its topological sort. Topological sorting. And I remember, I mean, yeah, it's a very important algorithm when it comes to, suppose I like you are, I will talk to you about data engineering, like how it fits into data engineering. How actually it's not limited to data engineering, but I am just telling you like how it fits into data engineering. Suppose you, or let's take anything. Let's say nowadays, uh, everywhere is we are talking about agentic workflow. So Suppose there is an agent 1, okay, and agent 2, agent 3, and there is a dependency. You said like, okay, first thing is, and let's say agent 4, okay. Now what happens? First, agent 1, let's say agent 0, takes query from user, okay, and now these two agents are basically, it will check policy, query, policy, and let's say it will check refund or something. So these two can work parallelly. And after that, imagine you have agent 2, that is basically some higher department that is going to check. Let's say it's a health insurance claim. Health insurance. I'm just trying to insurance claim uh, automation. So here is just agents are taking care of automatically. So you submit a claim, submitted claim, it will go to check and policy, and also it will check refund policy and all. Let's say these two things are different, or maybe it will check your documents. Check policy and documents. So both can work parallelly. It will check the policy and it will check documents, and after that, once these two are completed, then it will submit to higher authority, and they will take care of anything, these things. Okay, whether this request should be passed, and here if you will pass it, then it will credit money to your account. So here you can see the dependency graph, how it works. So if you talk about topological sort, now you have to like first agent 0 should be completed, and then only you have to complete these two things. You can do it parallelly, or you can complete them in any order. Once these are completed, then only you can complete, go to this node, and then you can go to this agent. So there is a dependency graph. This is known as directed acyclic graph, and you can decide like what should be completed first. So it's a simple graph, but in reality, you'll get complex graph where not like in, I'm not sure about agentic workflow how many agents they are using, but yeah, there are plenty of agents they are using. But in data engineering, if I talk, there are multiple activities that are happening, and so we create a DAZ, or you can say you DAG schedulers are there, and you can check airflow, Dexter, and all, but that's not related to here. So let's leave it. So I got it. Now next one is, okay. Next one is what? It's a hmm. So I just recalled the DFS, BFS, Topo chart, and shortest path algorithm. This is one. So shortest path algorithm. This Dijkstra algorithm. Dijkstra. What exactly we are doing in Dijkstra? Hmm. So Dijkstra. Kastra. Oh, DJI. Yes, KTRA. I mean, I don't know. Algorithm. So this is where what exactly we are doing. So we are using shortest path. So it is used for shortest path, non-negative edges. Wait, edges, wait. Okay, so what exactly we are doing here? So instead of normal queue, we are not using, so that we can make it efficient. So we are using priority queue. And what exactly we are storing? So we are storing distance. So if someone already completed, if the distance to reach a particular node is already efficient, then you won't process it. If you won't process the like other paths from which you are trying to access all the other nodes, so you don't need to re-explore. So this is how we are able to do it, and we are not using here normal queue and exploring all the options available. So this works. But when it comes to negative edges, what happens, like suppose every time it's reducing the weight, and because of that you won't be able to get the correct. And order of, I remember, not E log V. So I mean, yeah, we calculated while prior to Q, PQ we were using. So I mean, I will recall it later again, but E log V only, right? Let's do one thing. And another one is uh, what's name? Bellman code, right? Yeah. So now today I need to learn the Floyd-Warshall algorithm. So Bellman 4. Before that, I just wanted to know what are the Dijkstra's limitations. I forgot it. Dijkstra's algorithm. So first thing, I don't know, negative it won't be able to handle. Okay, that is okay. With negative it won't be able to handle. But another thing, what could be? I mean, yeah, let's just give. I'll give you one example. Suppose you are going to 0 to 5 and 5 to 3, and here is -4 and here is 1. So suppose you are going to 0 to 5, you move to 5. Now you will check its neighbor, and if you say, let's say 0 and 3, so its neighbor are 0 and 3. You will again check, okay, whether you can reach to 0. So you'll say, okay, if I'm moving 5 to 0, then you'll say, okay, 5 minus 4. No, no, no. -4 minus 4, 8. So you will get into trap where you will keep on processing the same nodes again and again, and you might end up with an infinite loop, or because every time uh, the new distance is getting reduced. It's not applicable everywhere, but some of the nodes will be having this issue. Some of the edges will be having this issue, so it won't work. Was it for the directed graph only, or could be used for, it can be used for directed and direct both? This is one of the questions that is popping into my mind. So I think it's for both. Let's think uh, why it could, how, like whether it's applicable for only one particular scenario where directed graph, is it applicable to directed only, or we can use it for directed and undirected both? So let me think. Directed and undirected. So if it is directed, then you'll be having single lays. So for example, 0 to 5, you move to 5, and you don't have anything to go back. So you won't go 5 to 0. Okay, but you might come from any other edge. That's why let's say 0, 5, 3, and 2. So 2, you are coming from here. Let's forget about this. 1, 2, and 0. That's it. 5, 2. Suppose you computed from here 0 to 5, you moved, and now again you are checking for this. So distance of 5 is 5, till 5 is 5. But now if you are moving from here, so 0 to 2 to 5, so it is 2. So you are getting better. So you will update it. So you need to use distance array, and how it will help in undirected. In case of undirected, if you will try to visit the same node again, for example, it's undirected. Let's say now, come on, it's not working or what? It, come on, man. Okay, suppose it is undirected graph. I don't know why. Yeah, it worked. So from 5, if you'll try to reach 0, earlier your distance was 5. Now it will be like 5 to 5 again 0, so 10. So 10. So definitely you won't go to 10. Suppose here is 0. Now you are reaching back to 0 with the 10 distance. It will say, "Are you stupid?" Why I'm writing it? So well. So this is then Dijkstra, and only thing is that Dijkstra can't handle negative. I forgot the spelling of DSA. What is it? DSA. I forget it, man. Okay, so it's done now. Let me recall. This is one of the problem. Like if you break consistency, because I started the last 2 3 days, I wasn't focusing much on DSA. Minimum application to reach end. Minimum multiplication. Okay, so Bellman Ford. Bellman Ford. Here if we have negative, but there is a condition like negative cycle should not be here. Okay, let's create some examples first. I know I got it like I have already watched video, so let's say 0, you are going to 1, 5, 3, and 4. Let's say this is one of the negative cycle means even so if you are repeating the operations still it's reducing the weight after n minus 1 relaxation. If we have v vertices, so what exactly we are doing? V minus 1 iterations to relax edges or weight. I mean edges or not. Hi bro, I'll type from here which one. It's taking different profile. Mm-hmm. Okay. Bomb. Sneak peek into my 9 to 5. Guys, I get motivation after looking into this. Can't mute. play music or let it be. We need to work hard, bro. Hmm. Bellman Ford algorithm. Huh. So what exactly we are doing in age relaxation? So basically, you will perform n minus one iteration to get minimum distance for each node. Maximum, it is max. So n minus iteration maximum like required to, and that happens when every time you are able to relax only one node, one of the node. Suppose, so what exactly it says, you have the nodes, right? And for zero, let's say zero, no, not here, zero, this is one, this is, oh shit, I haven't created all the nodes, zero, one, two, three, four, five. So let's say, let's take two like this, two, okay, and three, four, five. So these are the nodes. What do you keep every time? Infinity, 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 and for zero it will be zero distance. And now you start checking. Suppose if from zero you are looking for all its neighbors. Something wrong, I did, right? How are we relaxing the aces? For 0 to n minus 1, or let's say n minus 1 iteration. It's a simple iteration, and from 0 you can reach to 0 to 2, and you can, oh, 1 minute. We have age list, right? Age is different. So you can say 0 to 2 and 0 to 1, 0 to 3. I am able to recall it. So 0 to 1, 0 to 2, 0 to 3, 3 to 1, and 3 to 4. You can keep in any order. 4 to 5, and 5, and 1 to 5. And we need to relax these ages. So sorry, for example, if you are taking 0 to 2, that means you are making a move from here to here. So let's say this is one distance, this is two, this is three, this is zero. Let's say, no. I mean, let's say this is one, this is five, four, zero. Why I'm using zero? It's like two. In this way, from zero to two, you will move, and for zero to two, what will be the weight? So for the first stage, if you are going to relax it, now the problem is I kept the edges here. Let me do one thing. Speed up. Now I can see it at least. So 0 to 2. So you will say, okay, weight of 0 uh, plus weight of is, so it's 2, uh, will be new weight. Is new weight for a weight of 2. I mean, sorry, it's not weight, but the distance. Distance to reach zero. It's zero. This is distance array, and from here to reach here, the distance the distance or whatever you say, it's a 0 to 3 1. It's a, we are checking 0 to 2, so 2. So 2 you added, and distance of 0 plus 2, and new it will be distance of 2. So you will compare whether distance of 2 that you are calculating this is smaller than the existing one. If it is smaller, then you can update it here, and you will say okay, 0 plus 2, it's smaller than this, so you will say 2. Let's add it 2 here, and you will keep on performing on each edges. If you are getting smaller, then you will keep on doing it n minus 1 iteration. Even after it, if you are getting uh, like if you are seeing that any one of the weight is still reducing, not weight but distance is reducing, that means there is a negative cycle, and it will continue. So this is negative cycle detection. Anyway, so let's solve this Bellman Ford crazy. I took a lot of time to. I already solved it. 15th August, Happy Independence Day. I pronounced it wrong or what? Happy Independence Day. Yeah, it's correct. So I forgot it. So I will solve it again. So let me just see the description. Given a weighted and directed graph of V vertices and E edges. Given a weighted and directed graph of V vertices and E edges. V vertices, E edges. An edge is represented by AI to BI and the weight I. That means A to B, there is an edge and weight is WI. Find the shortest distance of all the vertices from the source vertex S. If the vertex can't reach from S, then mark the distance 10 as 10 to the power 9. Okay, okay. So exactly what exactly we are going to do. We are going to use Bellman-Ford algorithm because weights are negative. Why I kept Bell and Man alag? They are combined Bellman-Ford. Wait, let me just see. Is it name of someone? Mm, maybe Rutherford, Bellman Ford. Why the name of algo is Bellman Ford? Maybe here is Bellman Ford algorithm is named of Richard Bellman and Offset. It's two different people. Richard Bellman and Lester Ford, Jr. Junior, who published the foundational work on the shortest path method in 1958-1956. Just curious to which algorithm Google, oh, uses to find the shortest path. I'm sure they are not using this. Think Google Map does not use one textbook algorithm to find the shortest path. Instead, it uses highly optimized multi-layered system of graph traversal algorithm, pre-computed shortcuts, and machine learning models to calculate routes in milliseconds. The routing engine relies on a structured combination of several advanced A star, A strict. What is A strict search? A star search. Now yeah, they are saying A star. Sometimes they say because vanilla Vanilla Dijkstra. I'm saying I just heard the vanilla JavaScript or vanilla ice cream. So okay, it's out of topic. We are not here learning it, but let me uh, tell you. Okay. So our idea is simple. We have to use Bellman code. We have given some nodes here. Let me just draw 0 to 1, 1 to 2, 2 to 4, and 5, then 3, then 4, then 6. 6 minus 2, 3, 1, minus 3, minus 2, 5. And what needs to be done? We need to find the shortest distance for each. So what I'll do, simply I will iterate through all the edges one by one. I will keep distance, and if the node is not reachable, we need to keep 10 to the power 9. So that is the maximum distance for a node. So while I will do, okay, let me just tell you exactly what needs to be done here. Using the Bellman code, I will keep, okay, so these are the nodes 0, 1. It's better if I'll try to explain to you, then my understanding will be clear because that's the purpose of it. If I'm not able to explain, that means still somewhere doubt, I'm having doubt. Okay, so 0, 1, and 2, these are the different node, and we are storing the distance here because we need to calculate distance for each node. So I'm creating an array 0, 1, 2, 0, 1, 2, 3, 4, 5. So these are the basically index represents the node 3, 4, 5. Okay, now what I'll do, so they are saying okay, 10 to the power 9 you can keep if node is not reachable from any node, or at the starting we can say okay, this is the maximum value that we can store. So for 0 it will be 0 distance. For all other nodes you can say you will keep infinite. Instead of infinite, I can keep 10 to the power 9. Or let's do 10 to the power 9, 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 but and 10 to the power 9. So these are the distances at starting. And let's draw all the edges first. So we have 0 to, okay, let's follow the same order. Maybe, uh, okay. So we have 3 to 2. Okay. Another one is 5 to 3. Okay. Another one is 0 to 1. Another one is 1 to 5, 1 to 2, 3 to 4, and 2 to 4. Let me just check, double, I mean, just let me cross verify whether all the edges are there now. 1, 2, 3, 4, 5, 6, 7. 3, 3, 4, 6, 1, 7. Okay, so these are our edges, different edges. And now step is simply how many nodes are there. Total 6 nodes are there. So we need to perform for loop for the n minus 1, number of vertices minus 1. So n minus 1, that means 5 iteration. So let's do it. So 0th iteration, let me just first complete. For 0 you will say okay, we need to go to the node 3, 3 to 2. So for 3, what is the weight? 10 to the power 9. And you want to, so you will say, okay, so D, I'm just using word D here. D of 3 plus, so you want to reach 3 to 2. This one I'm processing, 3 to 2. And here if you see 3 to 2, what is the weight? This is the node that we are processing. We are trying, no, sorry. I'm 3 to 2. So 3 to 2, you are trying to reach here. So if you see the age weight is 6 and D of 3 plus 6, what is the value? So D of 3 is 10 to the power 9 plus 6. It will be bigger than 10 to the power 9, right? If you are adding something, 10 to the 10 raised to the 9 plus 6, and you are trying to make this distance, and for this one, so you are calculating this distance for D of 2. So you will compare with D of 2. It is 10 to the power 9. So definitely this number is bigger than this number, so you won't do anything. So it will remain same. And let's see now this for this node. 5 to 3. You are trying to reach 5 to 3. So let me clear this. And we are now trying to reach 5 to 3. So if you are trying to reach 5 to 3, that means D of 5, whatever the distance is, plus weight, age weight 1 is equals to nothing but you are trying to update 3. So D of 5, it is also 10 to the power 9 plus 1. This will be bigger than this 10 to the power. So we can say, okay, this one also won't update. Okay, now this is done. Let's say, I think I should not mark here. This is done in 0, that is done. This is done 0 to 1. Now you will try to move 0 to 1, and age weight is 5, and distance of 0 is 0. So D of 0 plus 5, you are trying to make this new distance for 1, D of 1. And right now, what is the distance of D of 1? It is 10 to the power 9. And here, this is 0 plus 5. So you will say, oh, it's better than 10 to the power 9. The 5 is better than 10 to the power 5, 9. So you will update here and you will mark it 5. Okay, so this is done for this. Now you will say, okay, this is done. Now you are trying to move 1 to 5. So this is done 1 to 5. And if you are trying to move 1 to 5, then you will say, okay, D of 1 plus what is the weight for 1 to 5 minus 3. Okay, so you will say D of 5. So D of 5, you will say D of 1 is now 5. 5 minus 3, 2. Better than the D of 5. So you will say 2. 2 will be here. Same we are going to do for this. And you will perform this operation. Let me do complete 1 to 2. You will check. So 1 to 2. Now you will check. So D of 1. D of 1 is 5 plus minus 2. So you will say 5 minus 2, 3. So D of 2 will be 3. And similarly, so this is done. Now you will say D of 3 to 4. So D of 3, we have 10 to the power 9 plus you are moving something 3 to 4 minus 2. So definitely you won't update because this is, you are already getting bigger number, and you, if you are adding or subtracting, it will be still be bigger. You can say it will be lesser than 10 to the power 9, but that is not relevant in this condition, to be honest. You can even take infinite at starting, and then you can update whatever the values that are infinite, you can update them with 10 to the power 9. Okay, now 3 to 4 is done. 2 to 4, we will say 2 to 4. So D of 2 is 3 plus 2 to 4, 3. 2, 3, 5. No. D of 2 is 3 and 3 and 4. So D of 4 will be 6. And the same, you will do it 5 times. And all the nodes will be relaxed, and you will get minimum distance for each node. So pretty. Sorry, bro. I was not looking into the screen. Actually, let me pop up the chat. Yeah, bro. If you are there, you can tell me. Okay, I'm just hi. So okay. Actually, I created one application using Cloud. So let me open that. It will be better. I'll see transparent chat. Okay. 10 p.m. start. Let me see. So here you go. Here you go. Live. I will copy this URL. You can ask me if you have any question. It will be easy for me to follow it. Will it connect? Yeah, yeah. Here we go. So let me change the opacity to minimize it so it won't. Actually, I haven't implemented it. I just asked Claude. Free version, by the way. So, okay. Now we need to implement it. And after it, I will jump into this problem, the second one, where you can see Floyd Warshall algorithm, and then we'll see if we can solve this problem as well. So let's first implement it. So we need to let me just recall what. Okay, let's see constraints by the way, and how much time will it take this algorithm? Time complexity. So we are performing order of n, and so n number of vertices and e number of edges, any comparatively better, where we were using e log v. There we were using e log v something. Okay. So distance. It's nothing but here I'll keep everything 10 to the power 9 into number of vertices. So v. I'm just keeping. Okay. So this is done. So we calculated it. Now I have to update distance of source. Here they are keeping source, not to 0. So we need to start from source. We need to calculate the distance for all other nodes. So here they have given source. They are not assuming like okay from they are basically not they are not telling like you have to start from 0. From source could be any node. So that's why I kept distance of s, not distance of 0 equals to 0. So here this is the primary step. Now we need to perform iteration v minus 1 1. So you can use I don't care about number, so I'm just using underscore a, that's why, and v minus 1 times. And here every for each edge we need to relax and we need to get the distance. So you can say a's have weight, so d of uh, okay, now we need to iterate through each edge. So for edge, basically I'm taking edge in edges, edge, not edge, edge, edges. So I got one edge, and here I will do one thing. Edge, I got edge. So edge will hold three things. First is AI, BI, and WI, something like that. What is it? AI, BI. So let me say AI, BI, and WI is nothing but edge. Here basically what I did simply from a list I'm just taking out all the different variables. So it's a shortcut in Python here. Simply is will be something like here. You can check it here. What are the values? For example, 3 to 6. So 3 will be AI and 2 will be BI and wi will be 6. So I got this. Now basically ai represents a node. It's better I will use this u, v and w. It's pretty intuitive. You are trying to move from u to v, and the weight for that particular race is w. So uh, definitely you will say new distance of v for the v will be d of u, whatever the distance, that is distance of. Okay, so basically what you are doing, you are trying to move from you are trying to calculate distance for v. So what you will say, okay, what is the distance for u plus this, the weight of this edge will be the distance of v. So you will say, okay, so I'm just keeping it in a variable d of u plus weight. And now I'll check if new distance is less than d of v, distance of v. Okay, if it is smaller than this, then you can update the distance. Distance of v is equals to new distance, and you will do it for all the nodes return distance. So let me just try to, okay, this is the condition. Here you kept distance of as 0. This is very simple algorithm. U v w edge, new distance u plus v. Every time you are calculating new distance, and if distance is smaller than the existing distance, new distance less than existing distance, then you will update it. Okay. Oh, let me submit it again. Actually, I already submitted it. What the heck? What is wrong with my output versus their output? If the graph contains negative cycle, then return -1 in a list. Ooh. One thing. Is it failing because of this? For me, it looks same. If graph contains a negative cycle, okay. So far we are not checking negative cycle. So I will do one thing. Check negative. Check if negative cycle. So okay. Why don't I keep it here? I don't need to keep another rate. Okay. And if I will do this thing, I'll use when only. And if I equals to v minus 1, if I equals to v minus 1, that means it is last cycle, and so still distance you are getting less smaller, that means break and found cycle true, found cycle false, true. You'll break this loop, so okay, it's okay. Break found cycle equals to true. That is okay, but something is wrong. I can sense it. I mean, whatever. This is also 10 to the power 9. What do you want? Oh shit. Somewhere I got smaller distance. 86. That's the issue. So what would be the reason for it? Hmm. Hmm, 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 hmm. So 10 to the power 9, I get the same into V. I got it. It's the process here. Basically, if I'll keep 10 to the power 9, it will keep iterating and you will get the wrong result. Is it applicable? Like, you should get the wrong result if distance of you. Distance of you not equals to 10 to the power 9. Wow, very good. Oh, sorry, I forgot to check. I still making same mistakes. Return if found cycle, return -1. Oh. It's like I'm making the similar mistakes again and again. I get trapped into the same. I need to revise it again for sure. Need revision and make sure I'm making a lot of mistakes, especially not checking properly the conditions, question, and corner cases. Let me jot down. So here, where? Okay, 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 okay. Let me do not here. I will say something. I will. Okay. What I was doing. DSA stream. I will go to this intro. Not basically first point. Points to remember. To remember. Read the question carefully. check the corner cases. Third, check dry run. Dry run, I hate it. Okay, another thing. Uh, Try to reduce the typo mistakes. Try to reduce the typo mistakes. Okay, perfect. Need a revision and make sure you are not making the same mistakes again. Forgetting the talk, forgetting the goal. So this is one thing. And let's jump into the Floyd Warshall. So this is an algorithm, and why the name is Bellman Ford. What was the name? Bellman, and there was another Ford. Let's leave it. Okay. So what I'll do? mm, let's see what exactly this. Maybe it's for cycle detection. Like if there is negative cycle, then how to handle. I'm just thinking. I'll be back. Just I want to. My border is empty. There is a little bit of border, so I just want to uh, fill the bottle and wash my face. I'll be back in maybe 2-3 minutes. I'll hardly take. So where is my screen? So I'm back again. Okay. Okay. So I'm planning. Once I will finish this Floyd Warshall algorithm, then I'm planning to ask ChatGPT to say, give me problems related to the Bellman-Ford, Floyd Warshall, Dijkstra. Definitely for Dijkstra, these are the problems. I wanted to understand it deeply. What are the applications of it? How can we use it? How to detect whether one thing for sure, like if this is related to shortest distance, you wanted to find the shortest distance to reach a node. Uh, you Right now I have two algorithms. One is Dijkstra and another one is Bellman-Ford. When to apply which, it depends on the weights of the nodes, weights of the edges. If the weights of edges are negative and there isn't any negative cycle, then we can apply Bellman Ford. Otherwise, if there is negative cycle, you won't get into the infinite loop, but the values that you are getting won't be the correct one. Okay, if there isn't any fixed path, if you'll keep on returning to the same path, it will reduce distance every time. So you will it will keep on reducing, and that's where Bellman Ford will fail. But but Dijkstra, if we have to identify when to use Dijkstra, when to use Bellman Ford, if the values are positive, then we can go for Dijkstra. I have a doubt. Why would someone go for Dijkstra if there is already pretty interesting algorithm Bellman Ford that is uh, maybe it won't be able to apply get the get the other things than the distance only. Let's see. Let me jot down the question. What Why do we need to use like DSA, SKTRA? I think discuss set DIS discuss tax discuss taxtra di distra 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 distra. No, yeah, DSA dice KTRA. Correct? Yeah. To use the extra if we already have better have better algorithm. Let's see. I'll check it. But for the time being, let's focus on virtual algorithm.
Shortest path algorithm, which is the deployed virtual shortest path algorithm. Now, this is very, very different from the Dijkstra or the Bellman that you learned, because Dijkstra and Bellman were a single source shortest path algorithm where you were given a source and you had to find out till all the other nodes the shortest path. There was only a single source. But when you talk about deployed version, it is different. Over here, there are 5 nodes. So from every node, be it from 0, 1, 2, 3, 4, from every node, you have to tell me the shortest path to every other node over here. If I'm asking you from 4 to 1, you should be knowing. If I'm asking you from 1 to 3, you should be right. So there are multiple source. Now this is why this is known as a multi-source shortest path algorithm. Remember this, it helps you detect negative cycles as well. Helps you detect negative cycles as well. So I hope pretty much you've understood what you need to find out. What is
So I'm just wondering if we wanted, we can do it using the Floyd Warshall, no, Bellman Ford as well, right? Every time we can change the source and we can apply it. So it will be order of n nodes n into uh, you can say order of n square e. Yes.
shortest path? Very simple. If I'm asking you from 0 to 1 and I ask you what is the shortest path in order to reach from 0 to 1. So you can take multiple paths. One of the path will take you 6. You can take this path, which is going to take you 5. You can take probably this path, which is again going to take you 5. Or you can take the shortest path, which is go here, go here, go here. It's going to take 2, 1, 1, which is an addition of, I think, 4 here. That's the 0 to 1 is 0 to 2, 2 to 4, 4 to 1. This is the shortest path. If I'm asking you, that's the difference. 2 to 4, shortest path from 0 to 1 is 0 to 2, 2 to 4, 4 to 1. This is the shortest path. If I'm asking you, that's the definition of shortest path. Any path that takes the least amount of edge weights is known as the shortest path. So what is the thought process behind the Gauss algorithm? Now, it's very simple. It states go via every edge, go via every node rather, or go via every vertex or node, whatever you wish to write. So it's very simple. It states go via every vertex and node. Go and drag, and get the shortest one. So for an example, let's take we want to find from 0 to 1, right? So if you're trying to find from 0 to 1, assume the distance you're trying to find is from 0 to 1. Okay. So what are the possible ways that you can do? You can be like, sorry, I can go from 0 to 1 directly. I'll be like, yeah, that does make sense, right? Because that's a straight away path. 0 to 1, if there's an edge, I go via that. That's one of the ways. But if I ask you, go via every vertex, then you can be like, okay, I can go back, go via 2. So what you mean? I will go to 2, and then from 2, I'll go to 1. Does that make sense? Yes. If I go from 0 to 2, it's going to cost me 2, and from 2 to 1, it's going to cost me 3, which will give me a total cost of 5, which is nothing but this particular path. That is if I go via 2. That is if I go via 2. Can I go via 3? I can. That will be something like, I'll go from 0 to 3, and then I'll go from 3 to 1, correct? If I go from 0 to 3, that's going to cost me 4. From 3 to 1, that's going to cost me 1, which will be a total cost of 5. Again, can I go via 4? I can go via 4. So if I go via 4, let me write that in white. If I go via 4, it will be 0 to 4, and 4 to 1, right? But 0 to 4, if you see, it's not direct path. It's a path via 2. Maybe someone would have computed, assume as of now, someone has computed that and given you from 0 to 4, it's a 3. Okay, so I'll be like, okay, 3, and from 4 to 1, it's a 1. So a total of 4. So apparently, we notice that from 0 to 4 and 4 to 1, it's taking me a cost of 4, which is indeed this 1. So what I did was, in order to go from 0 to 1, I tried out every different vertex. Can be 2, can be 3, can be 4. And apparently, I took the minimal path, and this is what it is. So the logic is very simple. Assume all the vertex are from, like the vertexes are definitely from 0 to n minus 1. So I can say all the vertex. So if I'm trying to look, can I say, if somewhere down the line, if this is I and this is J, and can I say this is nothing but I go from straight I to J, which is nothing but the edges. And can I say this to be K as 0? So can I write the path to be minimum of, if you have all the K's, it will be from I to K, very obvious, because you go from 0 to 2, and then from 2 to this, which is nothing but the J, correct? So can I write this plus J of K? I can. That's what the path is. From I to K I'll go, and from J to K is what I have to go. And if I take minimum of all of them, 5, 5, 4, minimum of all of the total vertex, then the answer, I'll have the answer. There's somewhere down the line I'm this, but I need to implement this on a wider scale. What do I mean by a wider scale? Because over here, 0 to 4 was not a direct edge. Because 0 to 4 meant it went via 2. So it was going via 2. So somewhere down the line, in the past, someone would have also computed 0 to 4, and they would have implemented via 2. Via 2, understand? So 0 to 4 could have been computed and stored. This is where you get an idea, okay, something like a dynamic programming, because we're using something which has already been computed. So you get an idea that, okay, this is a dynamic programming solution. It's not necessary that you know dynamic programming. I'm just saying, we're using something which is pre-computed. If I write it properly, I can write something which is pre-computed, which was, in this case,
Oh man,
this one.
I'm not getting
Because 0 to 4 was pre-computed.
I need to reverse.
As well, helps you detect negative cycles as well. So I hope pretty much you've understood what you need to find out. What is the shortest path? Very simple. If I'm asking you from 0 to 1, and I ask you what is the shortest path in order to reach from 0 to 1. So you can take multiple paths. One of the path will take you 6. You can take this path, which is going to take you 5. You can take probably this path, which is again going to take you 5. Or you can take the shortest one, which is go here, go here, go here. It's going to take 2, 1, 1, which is an addition of, I think, 4 here. That's the shortest path. So the shortest path from 0 to 1 is 0 to 2, 2 to 4, 4 to 1. This is the shortest path. If I'm asking you, that's the definition of shortest path. Any path that takes the least amount of edge weights is known as the shortest path. So what is the thought process behind the Gauss algorithm? Now, it's very simple. It states go via every edge, go via every node rather, or go via every vertex or node, whatever you wish to write. So it's very simple. It states go via every vertex and node. Go and drag, and get the shortest one. So for an example, let's take, we want to find from 0 to 1, right? So if you're trying to find from 0 to 1, assume the distance you're trying to find is from 0 to 1, okay? So what are the possible ways that you can do? You can be like, sorry, well, I can go from 0 to 1 direct. I'll be like, yeah, that does make sense, right? Because that's a straight away path. 0 to 1, if there's an edge, I go via that. That's one of the ways. But if I ask you, go via every vertex, then you can be like, okay, I can go back, go via 2. So what you mean? I will go to 2, and then from 2, I'll go to 1. Does that make sense? Yes. If I go from 0 to 2, it's going to cost me 2, and from 2 to 1, it's going to cost me 3, which will give me a total cost of 5, which is nothing but this particular path. That is if I go via 2. That is if I go via 2. Can I go via 3? I can. That will be something like, I'll go from 0 to 3, and then I'll go from 3 to 1, correct? If I go from 0 to 3, that's going to cost me 4. From 3 to 1, that's going to cost me 1, which will be a total cost of 5. Again, can I go via 4? I can go via 4. So if I go via 4, let me write that in white. If I go via 4, it'll be 0 to 4, and 4 to 1, right? But 0 to 4, if you see, it's not direct path. It's a path via 2. Maybe someone would have computed, assume as of now, someone has computed that and given you from 0 to 4, it's a 3. Okay, so I'll be like, okay, 3, and from 4 to 1, it's a 1. So for a total of 4. So apparently, we notice that from 0 to 4 and 4 to 1, it's taking me on cost of 4, which is indeed the shortest one. So what I did was, in order to go from 0 to 1, I tried out every different vertex. Can be 2, can be 3, can be 4. And apparently, I took the minimal part, and this is what it is. So the logic is very simple. Assume all the vertex are from, like the vertices are definitely from 0 to n minus 1. So I can say all the vertex. So if I'm trying to look, can I say, if somewhere down the line, if this is I and this is j, and can I say this is nothing but I go from straight I to j, which is nothing but the edges. And can I say this to be k, assume. So can I write the path to be minimum of, if I have all the k's, it will be from I to k, very obvious, because you go from 0 to 2, and then from 2 to this, which is nothing but the j, correct? So can I write this plus j of k? I can. That's what the path is. From I to k I'll go, and from j to k is what I have to go. And if I take minimum of all of them, 5, 5, 4, minimum of all of the total vertex, then the answer, I'll have the answer.
Wait, you are going from I, basically our goal is to go from I to K. No, I to J. So what you did, simply you went move from I to K and then K to J. So it should be K to J, right? Why J to K? If this is 0 to 2, 2 to 1, that means 0 to 2. Yeah,
So somewhere on the line up this, but I need to implement this on a wider scale. What do I mean by a wider scale? Because over here, 0 to 4 was not a direct edge. Because 0 to 4 meant it went via 2. So it was going via 2. So somewhere down the line, in the past, someone would have also computed 0 to 4, and they would have implemented via 2. Via 2, understand? So 0 to 4 would have been computed and stored. This is where you get an idea, okay, something like a dynamic programming, because by using something, it has already been computed. So you get an idea that, okay, this is a dynamic programming solution. It's not necessarily that you know dynamic programming. I'm just saying, try to relate. We're using something which is pre-computed. If I write it properly, I can write something which is pre-computed, which was, in this case, this one. Because 0 to 4 was pre-computed. It did not compute at the point. Someone already knew what was the value to go from 0 to 4. That is what we need as a pre-computation. So you pretty much got the formula. Now what I'll do is, I'll try to give you a sense of the graph, and then slowly and slowly, step by step, implement this algorithm so that you understand how is this algorithm implemented. Till now, in all the problems, we have been using the adjacency list in order to store the graph. But in the lecture 2, I've also taught you one more method, which is the adjacency matrix method. So you're going to use the adjacency matrix method in order to store this particular graph. Okay, it's very simple. In case you haven't seen the lecture 2, it's very, very simple. Something we know for sure is, if 0 is the node, and I want to go to 0 itself, the cost will be 0. If I go from 1 to 1, the cost will be 0. So from any given node to the node itself, the cost is going to be 0 no matter what you do, because you're already standing in the node. Something you do, 0, 0. So this portion will be storing the cost. So I can call this as a cost matrix. So 0 to 0 will be 0, 1 to 1 will be 0, 2 to 2 will be 0, 3 to 3 will be 0. So basically I'm saying this is 0, 0, 0. This is 1, 1, 0. This is 2, 2, 0. This is 3, 3, which is again 0. Pretty much understood? Right. Now what are the other? It says 0 to 1 is 2. So go to 0 to 1 and store 2. Go to 0, go to 1 and store 2. It says 1 to 0 is 1. So you go to 1, you go to 0 and you store 1. Okay. It says 3 to 0 is 3. So go to 3, go to 0 and store 3. Do not store the opposite vertex because it's a directed graph. It is a directed graph. If it's an undirected graph, one example, if it's an undirected graph and you want to plan and you want to apply this rod motion, just split this into something like this. 5, 5. As you see, dual direction edge, but with different values. In undirected, just make sure you assign them same values. Now remember, you just store 3, 0 as 3 because there is no 0, 3. Okay, nice. Next is 3, 1 as 1. So go to 3 and 1 and assign 5. Next is 1, 2 as 3. Go to 1 and 2 and assign as 3. Perfect. 1, 2, 1, 2 assigned as 3. Do we have any other thing? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, we have 3 to 2 as 4. 3 to 2 as 4. Done. So what I've done is I've assigned the cost. Make sure everyone else is infinity, which means unreachable as of now, which means unreachable as of now. So this is the initial cost matrix, which you can always derive from the given graph. Now you must be thinking, but remember, this is a TG, a directed graph. What if it's a UG? How will we implement the triad motion? Very simple. If there's an edge like this, it has a cost of 5. You say, okay, write this way, write this way. So this is how you convert a UG to a DG. Make dual direction edge. Similar to something like this. If you see over here, there's a dual direction edge, but with different weights. Okay. So if you have to apply triad motion in an undirected graph, just split that edge into 2 edges of same weights. That's how you can easily convert a UG to a directed graph. So this is the initial cost. Now what did I say? Let's, as of now, assume that I'm going to move via vertex 0. That's my first thing. I move via vertex 0. So if I move via vertex 0, I will have some upgraded something for sure. So let's start with vertex 0 and see what will be the resultant matrix that we will get. Now when I'm saying you have to move via the root 0. So can I say at first this is 0 to 0 stored as 0. Next is 0 to 1. So which means you're moving via root 0, which is 0 to 0 plus 0 to 1. Can I say it's similar to saying 0 to 1 because 0 to 0 will always be 0 and 0 to 1 is what you've already stored to. So you can just copy paste to. Next is 0 to 2. Can I say it's similar? 0 to 2 is nothing but saying 0 to via 0 by the way. Via 0 means 0 to 0, which is again 0. plus 0 to 2, which is nothing but infinity. So similarly, this will also be infinity. Why? 0 to 3 will mean 0 to 0 and 0 to 3. Similarly, this will mean 1 to 0. What does 1 to 0 mean? 1 to 0 means via 0 means 1 to 0 itself and then 0 to 0. Via 0 means that only, right? Via 0 means that because this is I, this is j, you're moving via 0. So can I say this one, this one, this one will just copy paste these values? Just go across, copy paste these values. Why? Because very simple. If your destination is 0, you can't move via 0. So whatever you're taking in order to reach 0, that is what you got. But what about these places? Let's tell them. So I'm saying this place is 1 to 2. I'm saying 1 to 2 via 0, which means 1 to 0 plus 0 to 2. Let's see the value of 1 to 0. 1 to 0 is 1. So I'll just write 1 plus 0 to 2 plus 0 to 2 is infinity. So that means it's an infinity which I do not need to write. So what I'll do is I will keep it as of now and whatever is the value. Because I know in order to reach 1 to 2, I'm taking 3. And if I go via 0, I'm taking infinity. So 3 is a better option. Let's keep 3. No, let's keep 3. Next one I see is 1 to 3. You see, next one is 1 to 3. Okay, so for 1 to 3, it will be, I'll go from 1,
1 to 0, 0 to 3.
To 0 plus 0 to 3. Now, what is 1 to 0? That's 1. Let's see what is 0 to 3. So 0 to 3 is again infinity. So if you go via 0,
Then
then again
infinity.
infinity. And for 1 to 3, are we reachable in 1 to 3? No, infinity. So let's stop this infinity. So similarly, I can say this is done. Similarly, what I'll do is I'll prepare the next case, which is this, which is nothing but 2 to 1. Now 2 to 1 via 0. Let's see. I'll go from 2 to 0. How much is it? 2 to 0 is infinity. So the patch will not be considered. Next, I'll do 2 to 2. So if I go again 2 to 0, it is again infinity, not to be considered. Next, I'll go 2 to 3, which will be via 0, which is again infinity, not to be considered. So apparently everyone else is infinity in this piece because it was previously infinity, now I'm getting infinity, so infinity, infinity. So next, let's see the next, which is somewhere this one, and this one. Okay, so 3 to 1. Let's see if we can get something better. 3 to 1. What am I saying? Via 0. Via 0. Let's see. If I go via 0, which is 3 0. 3 0 is 3. Okay, perfect. Plus 0 to 1, because I have to reach 1. So 0 to 1. 0 to 1 is 2. So that gives me a total of 5, which is already what I'm taking. So nothing better. Just copy paste the values. Just copy paste the values. So 3 to 1 is done. Let's get the next step. What is the next step? I'm saying 3 to 2, which means I'll go via 0, which is 3 0, right? Plus 0 2. Let's see. What's the value of 3 0? 3 0 is 3. What's the value of 0 2? 0 2 is infinity. Nothing better. We're already reaching 3 2 and 4. We'll keep going. Okay. So this is what happens if I try to go via 0. So via 0, I build all the paths. All the paths are built. Let's move to the next. So next one I'll see via 1. Let's go via 1 and see what is the new. Because remember, via 0 path has been built here. Via 0 path has been built here. I'll figure out the via 1 path now. Once I figure out the via 1, I'll figure out via 2, via 3, and so on. We'll get all the answers. So again, we know even if I go via 1, something I know for sure is these guys will be 0. Node to node. And anyone who goes 1, if the source is 1, for this guy, this entire portion will be nothing but this. Why? Because if you're trying to reach 1 0, it actually means 1 to via 1 means 1 to 1 plus 1 to 0. So you're actually going himself. If you're saying starting from 1, going via 1, it doesn't make sense. So you just copy paste whatever is there. You just copy paste 1, 0, 3, and infinity. Similarly, can I say if this is 1, the destination, it still doesn't make sense. Going via 1 and reaching 1, will that make sense? Going via 1 and reaching 1, will that make sense? No. They copy paste this so as well. 2, 0, infinity, copy paste. So now let's compute this, and this. 5 values required to be computed. Let's do. So first one is 0. Via 1 means 0, 1 plus 1, 2. Let's compute this. So 0, 1 means 0. Sorry, you take this 0 and this one, which is 2. So 0, 1 means 2 plus 1, 2. 1, 2 means 3. They get a 3, which makes it 5. What is the value already stored? Infinity. You are reaching at a better position. 5. Because via 1, you're reaching at 5. Much better, much better. Next, 0, 3. Via 1 means 0, 1 is 2 plus 1, 3. Let's see the value of 1, 3. So we take the value of 1 and 3, that's infinity. Now to be considered. So whatever is the value, we'll just copy this. Let's copy the value. Amazing. Next, let's erase this. Let's go to the next row.
2 to
Go
0.
to the next row. The next row, it's this one and this one, 2 0. So if I go via 2 0, that's going via 1.
2
Which is
to
2 1,
1,
and then going
1
1
to
0.
0.
Let's see the values of 2 1. So I go 2 1, infinity, not to be considered. So whatever is the value, we copy this. Still we have to figure. Next is this one, which is 2 3. So if I go via 2 3, it will be 2
2
1
to 1, 2
plus.
to 3.
It's plus.
Or
Nothing
2
but 1
to 1, 1
What
to
is 2
3.
1? 2 1, infinity again, not to be considered. Next, this is the next one 3 0. So if we take 3 0, that's nothing but 3 1 plus 1 0. Correct? So what's the value of 3 1? What's the value of 3 1 is? 3 1's value is it's 5. So let's write 5 plus 1 0. What's the value of 1 0 is? 1 0 is 1. So plus 1, which is 6. So as of now, what is the value of 3 0? It is 3. I'm already reaching 3 0 at a value 3. So why will I take 6? So I'll keep reaching directly. Reaching previously. What previous ways I've taken to reach 3? That's right. I need to take the new or previous portion. X is 3 2. Let's compute 3 2. So if I try to compute 3 2, it will be 3 1 again, which will be 5.
Via
8
1, via
plus
2. There are
1,
so many.
2, which is nothing but 3 this time. That's 8. So if you see, it's already reaching at 4. So why will I take the 8? So via 1, I have to build it. I have to build the matrix via 1 as well. Similarly, what you'll do is, you will go via 2, and then you will get a matrix. Using that matrix, you will do a via 3, and you will get an ultimate matrix. Whenever you get this ultimate matrix, this will be your shortest path between everyone. So if someone tomorrow comes up and says, you, hey, give me the shortest path between 3 and 0. So you go 3, you go 0, and you say, whatever is stored here, that's the shortest. So you can figure out from every node 1 to every node 2, the shortest path. from this ultimate matrix that is being generated. So what are we doing exactly? At first we're going by 0, then by 1, then by 2, then by 3. So can I say I'm going with everyone? And whenever I'm going by 0, I'm basically taking this, then I'm taking this, then I'm taking this, then I'm taking this, then I'm taking this. It's basically for this, taking this, for this, taking this, for this, I'm taking this, for this, I'm taking this. So in every iteration, can I say what I'm doing is very straightforward and very simple. And that's nothing but I'm going from I equal to 0 to the last node, and this is what I'm doing because I want to go from I to J. So this is what I'm doing at every node. Can I say this? Yes or no? I can. And what am I doing? I'm trying to go, for example, cost of ij. I'll take the cost as minimum of either what I have taken to reach it. That is currently what I'm taking. Currently, if I'm taking 5, I consider the 5 and I consider the new one via 1. So the new one via will be nothing but cost of I via whatever you're going via plus cost of that via of j. Can I see this? I can. And this is what I'm doing at every iteration. Every iteration. First via 0, via will be 0 here. Next via 1, so via will be 1 here. Next via 2, we'll get 2. And trying out everyone. Trying out this, everyone. And automatically these will be zeros because you initially you have assigned 0, so this will take care that it will always be zeros when you do comparisons. So what is this via? First it is 0, then it is 1, then it is 2, then it is 3. So can I say for via equal to 0, via lesser than n because 0, 1 to 3, every node in via plus plus is what this will be. And once you have done this n cube loop operation, at the end of the day, you will have your resultant matrix, which will be on. And so you see, we're pretty much derived this one for every iteration, and then we have wrapped it under a via because via will always change. Let's get to via 0, via 1, via 2, and ultimately the cost of ij will be storing your ultimate shortest distance. Now, a couple of questions. First question is how to detect a negative sign. What if the graph has a
What
negative?
is the
First question is
the algorithm is not much intuitive as the other ones. It is more of a brute force where all combination of paths have been tried to get the shortest path. Nothing to be panic much on the intuition. It is a simple brute on all paths. Focus on the three for loops. Okay.
is how to detect a negative cycle. What if the graph has a negative cycle? Because we know for a negative cycle, imagine a cycle like this, where we say, okay, it is minus 2, minus 3, plus 2. But the total costing is minus 2, plus 2, minus 3, minus 2, plus 2. Okay? Also, total costing is minus 3. So what will happen is the product costing will work properly. And it will figure out the path via 1, 2 to reach 0. So the costing of 0 and 0 will be minus 3. And apparently, the costing of any given node to itself should be 0 because the node will always be 0. And if it is anything less than 0, if the costing of any node, can I see this? If the costing of any node from 0 to n, very simple. If the costing of I and I, which is the node to node itself, is lesser than 0, I can always say negative cycle exists. I can always see negative cycle exists. Very simple. If we are going from all the nodes and node to node is less than 0, means Dart motion has gone by this and has reduced the cost from 0 to something lesser because of a negative cycle. And you know, if it has a negative cycle, it doesn't make sense to find the shortest path because someone will do unlimited terms and you just reduce it cost every now and then. So thereby, it's not possible for a negative cycle. So I hope you understood the explanation. Except to put it up. So as usual, the C++ solution is on the right and the exact similar Java code is on the left. So you need to find the shortest distance between every pair of vertices in a given.
Then so should I solve it now? Tarararam, pararam. What's time? 2:45. I feel like straight. Given a graph of v vertices numbered from 0 to v minus 1, find the shortest distance between every pair of vertices in a given. They haven't mentioned whether it contains negative cycle or not. Okay, no problem. Given a graph of v vertices numbered, so assuming there won't be any negative cycle, otherwise they would have told. Otherwise they have told like consider this, that, and all. So first thing, n number of nodes vertices can be up to 100. matrix value can be between -1 to 1000. Okay, -1 means there isn't any particular race or no connection between I to j. So we'll be given a matrix and it could be having some values. So let's say what is the input? A matrix, and we want to calculate the shortest distance from each node. So what you'll do, I will do one thing. I have matrix and I will compute for each node via each node. This will be j. Okay, each node. I will do one thing. So we are moving from I to j. So I will do what? I have given I have given j. Now I need to basically suppose I want to mat of I to j via k. What does it mean? It means matrix of I to k, matrix of k to z. And if it is smaller than the existing one, then you will update. So let's do it. I will. N is nothing but and now matrix. I don't need to use mem for okay. V in vertex, no, in range V. So via, I will say via in range V. Okay, I in range N, J in range N. If first thing, if mat of I to j not equals to -1. Okay, I to j not equals to -1. What? So, 1 minute, bro. I to j is not I to j. Suppose it's -1. That means we cannot take this path. So I cannot operate on the same matrix for sure. So what I'll do, simply I will create another matrix. I am thinking result is equals to, I will do one thing. Okay, so hmm, so for uh, I in range, let's do it in one go. Let's do one thing. I will do float of I in f. So starting I will keep into n. So okay, n number of so this will create one, and for underscore in range n. Now I'll do one thing. I'll copy the item. I in range n for j in range n. If a mat of I and j, so okay. If I equals to j, then mat of, not mat, but result of I and j equals to 0. Another thing, EL uh, if mat of I and j, okay, let's leave it. It will be the same. ELF mat of I and j equals to minus 1, then simply pass, because this is the value where you already have. Else uh, float of n. Else mat, else result of I and j is nothing but mat of I and j. Sorry, one mistake. Mat will become matrix. Matrix. Okay, so this is the starting condition. Then via I will I in range, j in range. If matrix of I, okay, I don't need to take care of it. So now if I'll say mat new uh, distance will be mat of I and mat of I to via plus mat of j via and mat of j. So if new distance is mat of less than result of I and j, then you will do a new distance result of I and j will be new distance, and here you will say return result. I just wanted to make sure everything is looking great. So first thing, I'm doing this. Do I need to do this? For I in range, j in range, if I equals to j, that means it's you are self is, but it could be, there could be weight 0 to minus 1. One zero three minus 1. 103 minus 1. It's 1 and minus 1 0 1, and 3540 3540. So these are the I could see here the pattern is like everything is zero. Self loop aren't there. But what if there is self loop? Will there be any issue? 0 to 0, 0 to 0. Okay. Zero to 4, 4 to 4. Right now I'm just assuming in such that everything is correct here. So I want to make sure everything I'm taking care of all the corner cases I in range n, j in range n. If I equals to j, that means I'm keeping it 0. Else, if matrix minus 1, that means I will keep infinity here. Else, result of ij is equals to matrix of ij. So yeah, that means this is the minimum weight for that node from direct node from 0 to 1, 1 to 3, something. And now we need to find out if we can get better weight distance from others. So I just started exploring matrix of v I to y, y to j, I to k, k to j. Result of ij, if new distance is smaller than new result of ij, new distance. V is not defined. Wow, perfect. Very bad. Somewhere I did something interesting. Result. Let's say blunder 0 to infinity, infinity, and 1, 0, 3, infinity. And infinity, infinity, 0, 1, 3, 5, 4, 0, 3, 5, 4, 0. This is our matrix. Okay, sorry, what's wrong? Hey, we have matrix. Now what I'll do, simply 0 to 2, 2 to, so this is the matrix and we need to calculate now. So first via, let's say 0, I will do it. So 0 to 0 and plus, let's say 0, 1, 2, 3, 0, 1, 2, 3. These are, so 0 to 0, it's a 0. Now you are saying like, okay, 0 to 0, 0 to 0, that means 0 only. Then 0 to 1, 0 to 1 you are traveling. So you will say 0 to 0 plus 0 to 1. Huh? 0 to 0 plus 0 to 1. And here you will say 0 plus 2, it will remain same. So similarly 0 to 2, 0 to 2 will be 0 to 0 plus 0 to 2, it will remain same. So for each 0 to 3 will remain same. 1 to 0, 1 to 0 you will say, okay, now 1 to 0 via 0. So 1 to 0 via 0. So you will say 1 to 0 and plus 0 to 0. 1 to 0 you will say. It will remain same. 1 to 1. 1 to 1 will be 1 to 0 plus 0 to 1. So 1 to 0. 1 to 0 is 1 plus 0 to 1 is 2. It's bigger than this number. Oh, sorry. 1 to 1 will remain 0 only. How can I get minus 1? Negative numbers, how? Somewhere I am I using the incorrect matrix? I'm returning result then. Crazy, something wrong is happening here. Printed. Then some blunder is happening. Not sure what's wrong. We are not getting distance minus 1 anyway. Let's do it then. Here result is okay. Then where is the problem? Damn. Why it is written your output 0, 2, minus 1, minus 1? Somewhere I returned it. It's written weird. Waiting 0, 2, 5, 6, 1, 0, 3, 4, 4, 6, 0, 1, 3, 5, 4, 1, 4, 0. What's wrong? Is it like result stuck? No misdicative values. Seems like letting if I'll remove it, then I need to use same. So I can use same, right? If it's same, okay, I don't need even to take matrix. So I got it. Now they are just referencing it and they are using it to take the values. Result of I via or result of not. I will do one thing. Let me mix, comment it. I will do one thing. Instead of result, I will use matrix. Matrix. Just replace blindly. Matrix of I, comma via or uh, plus 2 minus 1 or matrix of via comma j equals to minus 1. That means just continue, because this is the value where you cannot perform. It's infinite. Else you will say new distance this plus this. Oh, set. I'm making matrix here as well. Weird. If loop is working, not wow. What's wrong with my algorithm? I'm just iterating laying out matrix I in range n, j in range n. I kept this if matrix I, suppose we want to go I to j, and if I to j, and if I to y equals to minus 1, or y to j equals to minus 1, what does it mean? One of the distance is infinite, so new distance will be infinite only, or you can say there isn't any node from I to j. So right now we cannot go via this path. I hope it will change. Not changing anyway. How is that possible? Let's say 0 to, you are going to oh, 1, 2, 3, 0 to 3. So 0 to 3 via 0, 0 to 0, 0 to 3. So that's not going to help. Let's say 1 to 3. 1 to 3, you are going matrix of I and via k. A equals to, I'm just trying to matrix of cross I to via float of I in a if matrix of minus 1 else something crazy happening. Not working. I think I should take break better. Hmm. Crazy man. Bye bye.